welcome Colonel Shuey to the stage.
Increase in public affairs fee. Right. So, let's see, the topic tonight is football this weekend, right? When Air Force takes on Navy and Army in a couple of weeks, it's going to be fun. You guys are going to have a little bit of trouble because finally we can pass the ball. So, I'm not going to spend a lot of time on KCAOG, Kansas City Association Graduates of the Air Force Academy. Excuse me if I talk fast, and I'll try to get through this 13 pages in the next 13 minutes. But our organization was formed 15 years ago. We got 3 founders here tonight. Myself, Mr. Virg Saponsky, raise your hand, Virgil, thank you. And then Mr. Wendell Hartleroad, back there someplace, both football players. So, you know, we do have smart guys that go to the academy, but some of them do end up playing football, so what can I say? But anyway, these are great guys. We've been involved in this thing for 15 years. I also want to introduce quickly, if you'll just stand up. We've got some graduates from the Army Military Academy from West Point. Will you all stand up, please? There you go. Yeah. Thank you very much. We also have some Navy guys around here from Annapolis. Would you please stand up? Thank you, sir. Mr. Color back there is the president of the association, so he lets me play golf with him sometimes. And then we also have the Air Force Academy. I'd like to introduce those guys because we also have some special guests tonight, and I want them to know who's here from the Academy. Please, everybody from there. Some cadets. I'm up here in a dual role, giving the speech, of course, but I'm also in my 20th year, and tonight I've brought some candidates from the Air Force Academy that I'm mentoring. I'm the liaison for the Academy. I have 38 schools and a lot of kids that are really talented, that are interested in going, and several of them are here tonight. Would you please stand up? You've heard the reputation of the Air Force building the golf course first, and then the officers club, and then the runway. Well, that's because the Army and the Navy are jealous. The Army, when they go out and clear something for the golf course, they blow it up, so you have all these bunkers. You know, you don't play golf very well with 97 bunkers out there. The Navy is just jealous because they can't put a fairway and a tee on an aircraft carrier. So anytime you guys want to come and play on our courses, you're more than welcome. We enjoy that. We actually have golf tournaments about twice a year, and anybody who is in favor of our military, in favor of, likes, supports, really wants to be protected by, you're invited to come to all of our events, and we do all of our events jointly with the Army and the Air Force. So, I want to start with this one, actually. You've heard the reputation of fighter pilots who say they always start a story with, once upon a time, and this isn't no building. Well, I'm a fighter pilot.
There I was. No.
There I was. So, once upon a time, and this is no bull. There was a young boy who lost his dad when he was 5 years old. The grandparents came over and lived with him in the brand new house that Dad built before he passed on. And Grandma used to take the young lad out to watch the stars at night. And he got very interested in astronomy to the point that he knew he wanted to be something associated with astronomy. And then during the summertime, Flash Gordon was the TV show. Remember Flash Gordon? The old heads did? Well, Flash Gordon would go around the universe fighting the Emperor Ming with this beautiful Dale Arden on his shoulder, flying this cool little spacecraft that interestingly had smoke coming out of it, just like the Lionel train that this young man used to have. You couldn't figure that out. So these guys are in space and the train's down here. So anyway, being a space cadet was really something that was very interesting to him. So he studied very hard. 8th grade came along, he won an award with all the teachers voting on him. His picture was in the paper. And a colonel called him up and said, hey, I'd like to invite you to a party. It was a Christmas party. He went. There were young college kids there in this beautiful blue uniform. Turned out to be the first class of the Air Force Academy, 1959 graduates, soon to be graduates. So the kid said, hey, this is pretty cool. What's the academy about? The colonel said, well, let me tell you this, son. Here's what you need to do. So for the next 4 years, the kid did exactly that. Well, this is that young man with his ALO. It wasn't the colonel. The colonel was the regional liaison officer. This was Colonel Major Stevens. And Major Stevens said, you do these things so that for the next 4 years he did it. Guess what? Senior year, got a presidential nomination. President Johnson, who had been vice president, promoted up, he got to do the appointments. And the kid went to the academy. And so, first year, and guess who we met? Wendell Harbor Road. We've been friends for how many years now? How many decades? Wendell was the first classman. I was the dually. We didn't have friendship then. It came later. But anyway, we've been great friends ever since. So for 4 years, we did all this sort of stuff. And if you notice, right there, the kid is in the academy brochure as a pianist. I didn't play football, wasn't big enough, but I knew how to play the piano. So I was the accompanist for the choir and the chorale. And then, a few years later, after graduation, on the cover of Aviation Week and Space Technology magazine, there he is again, twice. Well, and then a couple years after that, flying the A-10 again, a couple years after that, into NASA for the space program. So what's the point of this? I give speeches to junior high school students and high school students. The speech is called, What's Your Dream? And I tell the kids, look, you've got a whole future ahead of you, but it's going to be wandering back and forth through failed situations unless you have a dream. You've got to figure out where you want to go. And a dream is nothing more than a wish unless you put a goal against it. And the goal is nothing more than an enhanced wish unless you have a timeline and you put an action plan together. Well, by accident, I actually put an action plan together. And these kids here tonight have done the same sort of thing. They have put their applications in for the Air Force Academy. Why would they do that? It's a $500,000 scholarship. All the books, tuition, meals, transportation, medical, dental, everything is covered for the next 4 years, plus you get half of the second lieutenant salary or an ensign salary. You get a guaranteed job for at least 5 years, 9 years if you're going to be a pilot. So that's why I've spent the last 20 years trying to educate kids to find those who are dedicated to become the future long blue line. And I also help, if they're interested in getting dirt in their teeth, sending them to West Point. Or if they really like to swim, sending them to Annapolis. We're kind of generic in that respect. So I support all of the academies. We have all kinds of events. But my point is, I had a dream. I made it happen, just like you would do if you have a business plan in your company. And so I tried to get these kids to think far enough ahead and do something with their life rather than stand there and do video games all the time. So that's my ALO speech tonight. Okay, let's talk about the STS. This is the most marvelous piece of equipment I ever ran against. Absolutely an engineering marvel from the very beginning. It was the first reusable shuttle spacecraft, and a spacecraft that was designed to go to orbit and bring stuff back. Now, Apollo was the end of NASA's career. Its charter was to take somebody to the moon. When it did that and finished, and Nixon canceled the whole thing, NASA had no place to go. They had tens of thousands of high-tech engineers, the best space people in the business. And they were led by bureaucrats. So what do bureaucrats do? They find a way to stay in business, right? Well, in this case, it was a smart idea. We needed to have some way to send all kinds of satellites and different kinds of experiments into space. So NASA came up with the idea of a space transportation system, STS. They wanted literally to be a commercial concern. But the shuttle was always experimental, so they were never able to get there. And it was their fault because it was always changing, and it was a very, very complicated piece of equipment. Notice there were 1 million piece parts on this thing, and there were 100 single-point failures. Now, single-point failure is if a part or a subsystem or a system fails, it's catastrophic. There's no way to fix it. The whole mission is done. We know about two of those, right? So industry and NASA goes to great extent to make sure those single point failures don't happen. Unfortunately, they can't create all the safety factors for somebody making a bad decision. And that's what happened with Challenger and eventually with Columbia. The shuttle was designed with 100 missions. We had 5 flyable. Shuttle should have had 500 missions. We only had 135. It was too expensive, $209 billion. But the aircraft, the spacecraft, was designed to be, I have a rocket up there. Technically, it's a missile. The rocket is unguided. This one has controls to fly wherever you want it. So it's a rocket to space. It's a satellite in the space, and it's a, well, you call it an airplane. It's a flying rock coming back down, but at least it guides itself like a glider. There were 6 total planes built, the first 2, Enterprise and Columbia. Enterprise never had the engines in it, and never had sufficient heat shield, so it never flew. Challenger, not Columbia. Challenger was eventually upgraded to a flight vehicle, but the first 3 that were really designed were Atlantis, Columbia, and Discovery. When Challenger blew up, Enterprise was built to take its place. And by the way, this is the 747 that was used to fly this puppy. Bob Crippen and Joe Ingalls, who I flew a mission with in the shuttle simulator, were the captive crew. They basically rode the 747 back and did all the test equipment, and then finally they did 5 of the free fall flights. So this is the first spacecraft to go up to orbit and bring stuff back. Flew a lot of missions, a lot of days in space, carried most of the people. Initially it was about $1.5 billion per flight. Eventually it got down to about 450 million per flight. And of course, with 2 crews of 7 each, we lost 7. Now there's something called MTBF, mean time before failure, and that's a percentage, or basically the number of fails that you should get in a block, like 1 in 1,000. So that would be 0.01%, right? Well, if you have 1 million pieces on board and you only have a failure rate of 1 per 100 mission, which is what the shuttle had, then all of those pieces have to be added together so that you only have 1 lost flight per mission. I mean, that's the probability that they compute. So that means all of these piece parts have to be very, very carefully built and bound not to fail. I had 14 opportunities in mission control. It was a great experience. Right there, the Air Force had our own back room, but I could go out in the mission control area. So when I see Apollo 13, that's the real Johnson Space Center. I was almost in the movie Space, but I had some other things, and they put the lieutenants up there, so that's okay. But I was on the 6th Discovery, the Challenger, the Atlantis, Columbia, the first and last Challenger mission, the satellite repair mission. I got to work a little bit with Kathy B. Sullivan. When you're going out and take something out of the shuttle, you've got to unhook panels, right? Well, if you use a power bolt retriever, guess what? When you turn that puppy on, you rotate around the device. So NASA had to develop tech tools that they could go up and that would not have that rotation problem. So there was much more involved and much more complicated procedures when you started fixing vehicles, and Sullivan was one of the first to do that. Then we got to Hubble, and they were proficient by that time when they repaired that mission. We also had the very first classified DoD mission. Everything that NASA flew that was classified was at the above top secret level. I had top secret for 25 years. I still couldn't get in. My clearance was being upgraded when Walker was caught, and they canceled all clearances from then on. So I never got to see what was inside the payload, but we know they're basically spy satellites. Okay, so about the STS. Space Transportation System consists of 3 parts: the orbiter, which you call the shuttle, the solid rocket boosters, and the external tank. It's big. It's more than half the length of a football field. Not as big as the Saturn V that sat outside my window, which was 363 feet long, laying on its side. That was a real monster. It's almost twice the size. But still, this is almost the size of the 747 as you saw in that previous picture. 4.5 million pounds of weight that has to be thrown into space at 17,000 plus miles an hour. That requires 7.7 million pounds of thrust. If it was equal, you'd never get up, right? And you could carry a max of 63,000, but they never went above 50,000. This is what this puppy looks like. The external tank, which used to be painted white, but they saved 600 pounds by getting rid of the paint. The SRBs, and of course the shuttle. I think that's discovery. Let's talk about some of the components because there's some interesting stories associated with it. You got two solid rocket boosters, 150 feet in length, basically. Again, half the size of a football field. They're 12.17 feet wide. That's important. By the way, there'll be a test later. And really, it's whether or not you can find that ticket of yours, okay? It weighs 1.3 billion pounds, but most of that is propellant, 1.1 billion. And it produces the majority, 83% of the weights, 5.6 to 6.2 million pounds. The difference in atmosphere. Boney burns for 124 seconds. Why? Because it's a Roman candle. Once the propellant's gone, ain't no more. And so, why keep it? You don't want to keep it, you throw it away. Okay, so that's what it looks like. Built in sections, propellant. 1, 2, 3. 3 sections where something called the O-ring, which you probably remember exists. There are 2 O-rings in each one of these compartments. There's a guy in Kansas City in 1920 named Joseph Potok, who was a scientist, and he was trying to make antifreeze. Well, he failed, like many scientists do, playing around with chemicals and mix it here and there and see what comes up. He made a slurry that turned into a rubbery substance that didn't have any value at the time. JPL found it years later, worked with Thiokol, gave it to them, or somehow it got over there. Thiokol decided, hey, this is a great binder to put in with the oxidizer and the fuel and make a solid rocket booster. They made the Minuteman with it. So SRB is son of Minuteman. That's how they make it. They have a 600-gallon drum, and they pour this stuff in. It's ammonium perchlorate and powdered aluminum, believe it or not. That's the fuel. And then this slurry, and they put it into this cast and make each one of these. Now, there's something else interesting about this. That's the SRB thrust. That's the main engine thrust. Notice the difference. 6.2 million pounds versus about 1.2. Well, that's for a reason, because you've got to get all of this mass up into space quickly, as fast as you can, and then you get rid of the SRBs, and now you've got the external tank and the main engine still pushing it to the orbital velocity. Note that note that the thrust vector is straight down the longitudinal axis of the vehicle. Means it's going to go straight up. Well, if you throw something straight up, it's going to come straight down, right? So what you want to do is get a pitch and roll program to push the shuttle over to the side to get into elliptical orbit. And you do that because the main engines are canted. So this is how you get directional control with the orbit. Now notice, you've got a little flame there, these are shock waves. There's only 1.2 million pounds of thrust coming out of these things. This is liquid hydrogen and oxygen. It burns very cleanly. You can't even see it when it's actually on fire, which is dangerous around the bucket. This has all kinds of particulate matter that's still burning as it comes out. That's why the difference between the two engines. The external tank is nothing more than a great big gas bag filled with liquid hydrogen and liquid oxygen. Hydrogen is the lower section, O2 at the top, and then there's a middle section in there that absorbs all the energy when the shuttle is shaking, rattling, and rolling. It's also very big, the biggest component. Very fragile, 58,000 pounds empty, but you got 1.68 million pounds of liquid hydrogen and liquid oxygen at 423 degrees below zero. Absolute zero is 459, and liquid oxygen at 297. Very cold, very big thermal problem. That's why you have this red stuff on the outside, hydrochlorofluorocarbon, which is a foam that tends to break off. It's not a good idea, but NASA never fixed it, unfortunately. This is what this thing looks like. Notice there's not really very much to hold on to, especially with a shuttle, so it releases pretty easily. Separates at 300,000 feet. It's got so much energy, it's 17,000 miles an hour at that point. It sails up to 668,000 feet before losing everything and falling back to Earth. And the velocity is so much that it breaks up in the atmosphere, disintegrates in pieces, and falls into the ocean. So this is not reused. The main engine is extremely interesting because this is the first liquid hydrogen oxygen engine that was designed to be reusable and throttleable, if that's a word. You can adjust it from 60 to 100% power. Only 400 to 490,000 pounds of thrust per engine, but that's all you need to get the rest of the speed for the shuttle. Pretty expensive, burns for 510 seconds. Why? Because you run out of gas. The external tanks are empty by that point. That's called MECO, main engine cutoff. And the pump that's on top of this puppy develops 75,000 horsepower. Now, you kids in physics, are you in physics? Okay. Horsepower is work, correct? Force times the distance. 1 horsepower is 550 pounds moved 1 foot in 1 second. 75,000 of them in that pump. The main engines themselves produce 37 million pounds of thrust, of horsepower, and the total with the external tank produces 82 million horsepower. This is one big piece of equipment. So, when we launch this puppy, we're burning 7 tons of fuel a second between the SRBs and the main engines. So, in 124 seconds, you're going to burn off 2.2 million pounds of solid propellant. You're going to burn off 1.63 million pounds in 8.5 minutes. And then you're going to start burning out the hydrazine that's on board the shuttle to circularize the orbit. Okay, so how do we put this thing together? Well, they had to build a special 747. They had to put structures in here. They had to extend the horizontal stabilizer and put the rudders out here because the shuttle is such a big hunk of drag. It's basically a huge speed brake. It blocks out the airflow back here, so the rudder that you would normally have for yaw capability doesn't work. Notice that this is at a high angle of attack. If the airplane is flying straight and level, the angle of attack is basically 0, theoretically, because that's the flight and that's where the nose is pointed. When it goes up like this, that's the flight direction, that's where the nose is pointed, that's the angle of attack. It has to do this because of the drag that the shuttle has. If it didn't do that, it wouldn't be able to fly straight and level. The external tank was built in New Orleans, and it's put in this huge barge shipped around the Cape. This is where it is inside the vertical assembly building, which I have been in at the very top on the catwalk, walking across with a steel grate looking straight down 525 feet. That's a little scary, and I jumped out of airplanes. So even, that's a little bit unnerving. But this thing is so big that you could actually put the Saturn V in it, which is what they did, and still have room. It's so big that it has its own weather system on the inside. You have clouds. 143 million cubic feet of space. There are 4 bays, so theoretically you could build 4 shuttles at the same time, which they never did. they only have 2 crawlers and they only have 3 launch platforms, so they're limited in other means in any case. Note this little guy. That's how big that external tank is. He's just a midget relative to the size of the thing. This is where the oxygen tank is. Right in here, there's this third dummy tank, and that's where the liquid hydrogen is. So they bring it in, they haul it up vertically. They've got a 250-ton crane that lifts all this equipment up to the very top. They bring the crawler in with the mobile platform on top of it, which you'll see later. It's already about 50 feet high by the time they get the whole thing put together. They put the 2 SRBs on it. They lock them down with 8 bolts each. And the bolts, that's pretty big, right? The bolts are 3 times the size of this, 3 times the diameter, and 28 inches long. And they have explosive nuts on them, which you don't want to play with. My brother would, but he used to buy dynamite to go blow up trees as a teenager. Anyway, so here we are. We got the SRBs loaded. You can't see the mobile platform or the crawler. They've got the external tank now mated with the 2 strut supports. And now we're going to put the main engines inside of the shuttle in the shuttle assembly building. I've got different buildings around it. This has all kinds of valves and sensors and connections. You got to bring 2 big pipes in for liquid hydrogen and liquid nitrogen. The hydrogen comes in and cools the engine, so you have different plumbing there. And that's all got to be mated. This probably has to be really perfect. The metal here it's so hot, 5,700 degrees. They had to come up with a brand new type of metal so that burner can could withstand the pressure and the temperature. This thing gimbals. In other words, it moves around just before launch and during flight. So it's got to have mobility to it. There's all sorts of things that are involved with this main engine. They bring the shuttle over on the carrier, put it in a cradle like this, and then they raise that puppy up a whole bunch, bring it over to the assembled SRB and external platform, lower it down. Now you see how this thing is almost the size of a 747, and you still have all of that space up at the top. I mean, everything they built was unbelievable to me. So there it is, all made it up. You got game plans all around to fix things, to repair things if necessary. Hopefully nothing can be repaired. And now you have a payload building that is assembling or is bringing in and putting into the carrier the satellite or whatever they are putting up in space. Skylab in some cases. Well, it wasn't Skylab, but part of the ISS. And a lot of that is all wrapped up, so very few people get to see what's in it. It's put into this carrier, brought out on a payload carrier, just like the crawler is, that I'll show you. And it's raised up. This whole thing swings over to the platform. So you can imagine all of the weight that has to be on that hinge. Another engineering marvel. They bring that over. Well, here's the crawler coming out to the pad. The crawler itself is about 25 feet. See the people down there? 25 feet here. The whole platform is about 30, so we're talking more than 50 feet. This thing, the crawler can carry 18 million pounds. It's not loaded, so we're only talking a couple of million pounds. It takes 30 people to drive this thing out there. It takes it takes 6 to 8 hours to drive out there. I never figured out why they didn't do this in a curve. It must have been, I'll tell you that later. But anyway, this thing is amazing. It goes 42 feet per gallon of gas. All 42, not 43, not 41, but 42 feet. And so that means it takes about 457 gallons just to get out to the launch site. It's an all-day affair. Well, you don't put the launch site down on the grass because you've got a little thing called hurricane, right? And you've got all sorts of stuff underneath there, some regular buckets for the flames to come out. So they got to build that out. Means you got to have a ramp. No escalators available. 5 degrees. So all of the crawlers have to be built with hydraulic jacks, 16 on the shuttle, so that they keep that perfectly vertical. So they've got to raise the rear end up 5 degrees and then lower it as they get to the technical. It's just another of those engineering marvels that you never think about when you're sitting there watching the show. And you notice that it's waiting for the shuttle, it's waiting for the payload to get in so it can put it in place. And there it is, it's all raised up now. Okay, so here's Discovery. This piece up here keeps the oxygen, liquid oxygen, from forming ice crystals, which would be really big, and it would come down and hit the nose, and that would be another Columbia accident. So that all is all designed. This is the crew compartment. There's all kinds of umbilicals that come in, which are snapped away and fall back, and then are quickly shut behind a door during launch so they don't get burned up by all the flame. But this is really hot. Okay, so launch operations. What are we going to do? Well, there's all sorts of procedures and all sorts of people. Mission control, you've seen the movies, of course, those are guys are all sitting there with the medical and the fuel, and it just goes on and on and on. At 31 seconds, the command is sent over to the onboard computer. So now the computer inside the shuttle is controlling everything. At 10 seconds, you get all these sparkles. You know, you've seen all those little hot things. Well, that's hot zirconium that's being shot by 4 of these little solid engine jets. And the reason they do that is because any of the hydrogen that's leaking out, hydrogen is a really small little piece of atom. So it's pretty easy for that stuff to leak out. They want to burn all of that off so they don't have an explosion and then have a big boom boom when the shuttle would explode. So they burn that off for about 40 seconds. 6.6 seconds, then they open the valves and they start bringing hydrogen down through the pump. It also goes around the engine to start cooling it. And because it's so cold, when it hits the metal inside that pump, it immediately vaporizes and starts building pressure. And the pump spins up to 30,000 RPMs within 3 seconds, which is really amazing. 37,000 in 5 seconds. All the sensors are measuring what is going on, if they got the right amount of pressure everywhere. And then the igniter is fired, and all of a sudden you start getting a buildup. You see how the nozzles shake. That's because it's a little irregular as to how the gas is coming down there. And so they've already gimbaled the nozzles. They've tested it in that 30 seconds before to make sure that they're all working, nothing's frozen up. And then they spread the nozzles out so they're pointed as far as away from each other as they can so they don't bang into each other when you start the engines. The main engines are started 120 milliseconds apart. Somebody figured that out. I don't know the reason, but it sounds like a good idea. And then as soon as it builds up at 90% power only, then you start getting that asymmetrical thrust coming from the angled main engines and starts pushing the shuttle over. And it literally bends the shuttle 6 degrees at the top. But it's a mechanical spring, so to speak, and the shuttle automatically springs back. If all the sensors read right pressures and all the other values that they need to meet the minimum standards for, then at 0, when it actually reaches the vertical, command from the shuttle fires the explosive bolts, nuts off of all 8 of the bolts, and you're not going to stop the shuttle anyway with 7.7 million pounds of thrust, but they don't want to do any damage. So anyway, it fires off the bolts. Now the shuttle is free. It fires the igniter in the top of the 2 SRBs. That fire goes all the way down to the bottom in a quarter of a second. So you have the entire SRB lit off. and suddenly you have 6.2 million pounds of thrust coming out of the shuttle. The SRBs plus the 1.2 million from the engines. It's going up into space whether you want to stop it or not. At 8 seconds, it clears the tower and is going 100 miles an hour. At 1 minute, it's going 1,000 miles an hour. At 2 minutes, it's going 3,000 miles an hour. And it's burning gas at 7 tons a second. So now you've also done the pitch and roll program, so you're pushing the vehicle over to the side. 124 seconds, the SRB runs out of propellant, and so it's kicked off, explosive bolts fire, and they push away. So it travels, since it's going 3,000 miles an hour, almost straight up. It's now going to rise and eventually fall. The parachutes open up, and it's going to fall in the ocean and be retrieved and then refurbished. The main engine is continuing to burn fuel from the external tank for 8.5 minutes, and it's accelerating because now you don't have that extra 2.5 million pounds sitting on your wing. And as the fuel burns down, it gets lighter, it goes faster and faster. So by 8.5 minutes, when you get MECO, main engine cutoff, you've heard that. Assuming you now you're doing 17,000 miles an hour.
Sorry about that, folks.
A near orbital trajectory. Now, there's a couple of interesting things historically about this, especially if you have seen the movies. You know a guy by the name of Werner von Braun, German scientist, who was the genius that built the V1 and V2 for the Nazis. Well, I gave him a pass because if you don't work for the Nazis, you don't get to live. So, that's how things go in old Nazi Germany. But anyway, under Operation Paperclip, he came over here to the United States with 1,000 other German scientists. Fortunately, we got him, because all the rest went to the Soviet Union and did not have a good time. So von Braun, as they developed the space program, we had one-shot rockets initially, and they would go up and then disappear in the ocean. He realized if we're going to go to the moon, you have to have a whole lot of power, a whole lot of energy, a whole lot of fuel. Well, why drag all of this extra weight up from empty gas bags and engines if you don't need it? So he developed the multi-stage rocket, where the first stage would burn out. You'd throw the engine and the tank away since you have no more fuel. You ignite the second stage, and then the third stage, and maybe the fourth stage. That's what saved the space program. That's why you could go to the moon. That was one brilliant piece of technology that was developed. Another one is, if you saw the movie, was invented by a lady by the name of Katherine Johnson. She was in the movie Hidden Figures. A black lady who got to go and work with Mr. Gilruth, I think his name was. It was the guy that played. Pardon me?
We're trying to think of the name. We sold it.
Yeah, okay. So anyway, here was the problem. NASA engineers couldn't figure this out. If you go straight up, you come straight down. If you are in an orbit, it's called an ellipse. There's an equation for an ellipse. Everybody knows that from geometry. There's also an equation for a parabola. If I throw this out to the audience, it's going to rise up, slow down, and then come back down, thanks to Sir Isaac. It's called a parabola. Well, the problem is getting a parabola equation turned into an elliptical equation. It's not that easy. NASA couldn't figure it out, but Johnson did. She was a very smart lady. And she was the one who was able to not only figure that transition out in orbital mechanics, it's called a Raman transfer, but that's when you go from one orbit to another. I don't know what they call this, a transition from a parabola to ellipse. But anyway, she figured that out. She also confirmed the orbit of the orbital mechanics for John Glenn's flight, and she saved Apollo 13 by figuring out where they needed to land. And of course, she became very famous down there. She was gone by the time I showed up. But all that sort of stuff is very interesting, because individuals are the reason, just like Sir Isaac Newton, we didn't have calculus. Euler may have invented it. But we wouldn't have a lot of this high-tech stuff if it weren't for these really brilliant people. Okay, so, exactly one more. So let's pretend that you are sitting in the command pilot seat. You're going to fly this thing to space. Actually, the computer is, but we'll pretend like you won't. So we've taken off, and we've already launched. We're in space now. There's the SRBs. We're at 1,500 to 400 miles up, the upper range of the shuttle. Hubble flies at 360. Anything you want to stay in space for a long time, push it up. If you want to stay out there forever, well, almost forever, you put it in a geosynchronous orbit, which is at 19,000 miles up in space. The Fleet Satcom satellite that I worked on was the first geosynchronous communication satellite that gave the president worldwide communications capabilities with all the ships. Thank you very much, Navy. So you've got to park it way out there. That's a whole lot of energy. And the way they do that is they launch the vehicle in a highly elliptical orbit, not circular, but elliptical orbit. When it gets out to the top, they have a motor, a solid state, solid rocket motor called an apogee kick motor. They fire that, they give them extra energy, and that circularizes the orbit. But once you're out at 19,000 with the shuttle, you're not going to fix anything because they can't fly that up. So anyway, that's some of the tricks that they use in orbital mechanics. Also, when you're on getting to orbit, or you're on orbit and you need to move the spacecraft around, reposition it, you have 44 different thrusters in the nose and tail. And they're just little jets that use nitrogen tetroxide and hydrazine. Nitrogen tetroxide is the oxidizer. Hydrazine is the propellant. Hydrazine has an interesting technical problem in that when it freezes, it shrinks. When water freezes, it expands, right? So if you put water in a bottle and it's not very strong, it'll explode. Hydrazine is the opposite. Discus was one of the satellites that was in work down the hall for me when I was working in Fleet Sat, and they had a heater that failed. You have to have heaters on these lines because it's so cold in space, 300 degrees below zero, things freeze up, and hydrazine will freeze up. So you have these heaters using solar energy through the solar panels to keep these things warm. Well, one of these heaters froze, and it created a solid propellant in the line, but the hydrazine kept flowing over. So when it went back into the sun and heated up again, now that plug, which has been filled in and locked up as a big rock of ice, now it failed and burst the line. Well, burst line is nothing more than a little jet. It spun up the vehicle. You can't fix it, so you've lost a $500 million satellite because somebody didn't check a heater. And space just has all sorts of issues like that. I mean, it's very difficult to work in. Okay, so we've got 2 pilots, as many as 6 other payloads. Typically, they only have 7 or less. Only one mission had 8 pilots. Lots of living space, right? That's cubic feet. That's not much. We've got 3 decks, the pilot and 2 payload specialists sit in the flight deck during launch. And there was one mission that Dick Covey was on, my classmate. And he said that they had canceled the day before. They went out, it was still raining. The next day, he thought they were going to cancel, but they were ordered to go in the space shuttle, so they all got strapped in. And there was a big hole, weather hole was going to be probably some hours, so the guys in the back unstrapped and went to sleep. Now, Dick is with Joe Engel, the very first shuttle astronaut, and they're playing the game because they're the contact with mission control. So all of a sudden, they got launch approval. They had 9 minutes to get together. The guys in the back were fumbling around trying to, in a spacesuit, you're trying to get all strapped in. Well, you're not going to stop the launch. So they took off, MECO started, and when MECO stops, right, you're not going to fire the engine until another 9.5 or another minute and a half. All of a sudden, here's something in the back. This guy says, it was lounge, astronaut lounge. He says, wow, this is really cool. He looked back there, and lounge is floating around in the cabin. He never got strapped in. the guy got fired and couldn't bring me back. This is my favorite part of the space shuttle. Like I mentioned, I got to fly a simulator mission with Bob Crippen and Joe Engel, the very first two shuttle pilots. They only flew the approach because on takeoff, well, they had different profiles, but they didn't do takeoff this time because it's all computer controlled. Anyway, this particular mission, the mission control sim operators gave an undercast, so you couldn't see their runway, you couldn't see anything, and they're flying the computer around. All of a sudden, they have a failed MMU, the computer failed, so you don't have any directional control. So they're rolling out on final with nothing but clouds underneath them and no computer to tell them what to do. But they knew that they were on glide slope and on heading before, so they looked at each other and I thought, this is going to be interesting. And they said, well, what the devil? So they punched through, and all of a sudden, they're really steep. And I'll tell you about how steep this is. And they looked at each other and said, man, let's try it. So they pop the speed brake real early. They're screaming down, and they pull out, flare the spacecraft. They land long, flies off of the runway and out into the swamp. And the shuttle simulator just goes ahead and throws the airplane down, and just like it's a real thing. So they said, we got it down, didn't we? 2,020 different switches, circuit breakers, panels, displays, you name it. Now, I brought my -1. Every pilot has what's called a -1, which is the pilot training manual for their aircraft. The bigger the airplane typically is, it's a little more, but this was for the OV-10. And that's not a very complicated airplane, but pilots have to learn, pretty much everything in here and memorize a lot of the emergency procedures. The shuttle astronauts, the command pilot and the pilot, have a stack this tall of manuals that they have to learn. That's why it takes 2 years of training to make sure that they have enough skills to fly this vehicle. And they fly 1,000 landings before they're qualified. They have a Gulfstream 2, which they take up to altitude, specially modified, it's got a speed brake on it, and they dive down with the gear down, and it's stressed to handle this, and the engine's in reverse to simulate the shuttle. And then they get down to the runway, they have an instructor on board, and he says, when it's 26 feet, eye level to the command pilot, he says, go around. And that's a successful landing. And many of those. So, this is really fun. These were updated in about the 1983 time frame. It used to be a lot coarser. This is the MMU. Basically, he flies a box around a little circle, and if he keeps that box right there, then the computer is telling him exactly what energy to fly all the way down to touchdown. All right, so we've got the flight deck, the mid deck, the lower deck. Oh, I got the right one. So you are at 115 miles. You're doing 17,200 miles an hour. You're over the Himalayas. You got 5,000 miles in 65 minutes before you land, and you hope that the computer is right because you're not going to touch the stick for a long time. And so here's what happens. You've got to lose airspeed. You've got to lose altitude. The very first thing you do is, and you're going that way, you're going to turn the vehicle around, sort of like this, and fire the OMS engine. You notice you've got these two little engines down here, and then there's all kinds of little engines, 44 of the thrusters. The OMS engine throws out 6,000 pounds of thrust per, but this is a 200,000 pound vehicle, so it's not going to do very much. You're going to burn it for 3 minutes, and you're going to lose 200 miles an hour. Big deal. What about the other 17,000? As soon as you get the velocity reduced, you're going to flip the airplane over, spacecraft over, and they're going to start coming down at 18 degrees glide slope, maybe as much as 20 degrees, depending on your initial altitude. That's steep. and you're starting over the Himalayas. You're going to be at 400,000 feet over Hawaii, 600 to 400. So the only problem is, if you do this, you're going to have all the heat up here. So you want to have this at a 40-degree nose high angle. So all the heat and speed brake, so to speak, is right on the bottom of the airplane where all the tiles are. By the way, the original vehicle had 30,000 tiles on it. This one, after about 4 or 5 launches, had 24,000. Every tile is between a half an inch to 4 inches thick, roughly on the average about 6 inches square. Every one of the 24,000 tiles is unique. It has its own number. It has to be handmade. Every one of them takes it takes about 10 days and 45 man-hours to replace one tile. Typically, you would lose 30 to 100 on a mission. The worst example was when they had a serious issue. They had 4,000 tiles they had to replace. And this is the only thing that keeps you between life and hell, basically. Okay, so you're at a 40-degree angle up. You're flying through 400,000 feet. You're starting to sense the atmosphere. Some of the air molecules are impinging, starting to heat things up at that 18-degree glide slope. Then you've got a whole lot of altitude and airspeed to lose. If you do this, you're going to drop the nose because there's no lift. If you do this, this is going to start flying again. You're going to skip out the atmosphere, lose your altitude, come down, and eventually you're going to basically crash far short of the target. So you've got to have a combination of the two. So NASA has the shuttle do an 80-degree bank and a bunch of S-turns like this. Just like if you put the hand out to the window when you're going fast. 4 S-turns. So you lose a couple of 100,000 feet. At 200,000 feet, you're still going at Mach 25, 17,000 miles an hour, but you're slowing down. At 150,000 feet, now you're starting to pick up, and you're about 140 miles out. You're about Mach 5, and you're starting to pick up the TACAN. TACAN is tactical air navigation that pilots use. There are 3 systems on board for the shuttle, plus later on they had the GPS. So now the onboard computer is not trying to put the vehicle into this big basket. Now it's got a specific target attacking at Kennedy Space Center that it's going to use for its navigation. At 120,000 feet, the ailerons, which are these flaps down here, and the rudders start becoming effective. So you don't need to push the vehicle just with the RCS, the reaction control system engines, which typically push the rear end, not the front. Now you can start flying the airplane like a glider, sort of. Glider that's really heavy. At 1,700 miles an hour, now the computer starts computing based on energy maneuverability. You've got airspeed, which is fast, you've got altitude, which is high, and you've got distance. That's all you've got. You can point the nose, but you have no engine to fly this thing with. So the computer is figuring out what combination. This is potential energy. Airspeed is kinetic energy. The combination gives you a total energy system. So now you're looking at all of the energy required to do this big circular path right down to the runway. It's going to manage the system. It's going to make sure you're not pointed too far away or too high or too low. So all the computer is doing is measuring that and putting that little ball in that space. 50,000 feet is when the pilot finally takes over. All the way from the Himalayas to 25 miles short of the runway before the pilot handles this thing. Hopefully, Microsoft didn't invent the software. So, pilot takes over 50,000 feet. That's you, right? So if this is my runway, I'm coming, and we're looking down the top, I'm coming over here 25 miles out at 50,000 feet. I'm going to turn around, curve, still descending, at 90 degrees to the runway. I'm now at 20,000 feet. Now, an airliner at that point would be about 3,000 feet. So we are way up there, falling like a rock. Then we're going to fly around at final approach speed. When you roll out on final, now you're at 10,000 feet. You've lost 10,000 feet and the last part of your airspeed, so you're 345 miles per hour on final approach. 7.5 miles from the runway, still at 10,000 feet. So you're coming down at 18 degrees. An airliner flies about 2.5 degrees. So you're still steeper than snot. At 2,000 feet, now the pilot pushes the nose up and goes into a pre-flare maneuver. He's going to slow the aircraft down, and he's going to stop his descent rate down to where he's only got a 2.5 degree descent rate, still falling. At 300 feet, about 8 seconds before touchdown, the gear comes down. 8 seconds before touchdown. So it's all automatic. So you put the rudder in. You cross the threshold of the runway, the end of the runway, at 26 feet. Not 25.1, but 27.3, 26 feet. And then you touch down 2,500 feet down the runway. And by the way, by the time you enter the approach end of the runway, because this thing is nose high, it's pushing all the air, and you're starting to get ground effect. It's basically a cushion, just like you put your hand out the window, right? It's pushing. So the ground effect actually aids in landing the aircraft. You typically see really good shuttle landings. Ground effect is one thing, 1,000 landings doesn't hurt. So you land 2,500 feet down the runway, you pop the drag chute that comes out, the nose comes down, and you release the drag chute so it doesn't fall on the engines that are very hot, would cause them to light off and burn. You put the nose brake down, you come to a full stop, hazmat comes out with the ground crew, make sure there's no hydrazine leaks. You come out of the cockpit and you're a hero or a heroine. Congratulations. That's the problem. So briefly, let's talk about what NASA didn't do right. I unfortunately was there in mission control with Dick Cuddy, as I saw my classmate who also with the Hello Repair mission. He was the voice of mission control. Houston, this is challenging. And Dick, I've got movies of him, and he was just as distraught as everybody was. It was a major psychological episode for everybody at NASA, and of course the nation in general. So what happened with Challenger? Number one, there were icicles about that long on the launch platform everywhere. There was ice everywhere. And the temperature was 27 degrees. The launch limit was 39 degrees. NASA wanted to fly because they were pushing to be a space transportation agency. Their goal was to have 16 flights a year. The max they ever flew was 9. Typically, they would have 7 or 6 or fewer, depending on the missions. But they really wanted to fly this mission, and they tried to push the Thiokol manager into saying, yeah, it's safe to fly it, and he wouldn't do it. And I know that because I called him up, and I talked to him, he sent me his book. He says, we have not tested this vehicle at this temperature. We don't know what's going to happen. We will not sign off. So NASA flew it anyway, unfortunately. And so what happened is that those rings, those O-rings, shrank. Now, when the shuttle fills up, when the external tank fills up with liquid hydrogen and oxygen, it's on more or less springs, mechanical devices that are flexible, because the tanks shrink 6 inches with that cold stuff inside. So you have to have the ability to support that. All that weight without it breaking and without it cracking and so forth. So everything about the shuttle is a major nightmare from an engineering standpoint. Thermodynamics, mechanics, astrodynamics, you name it. So anyway, the O-ring shrank. Then you've got 1,000 psi pressure on the inside, 4,500 degrees. And so it pushes everywhere. You know, a balloon pushes all the way around, right? PV equals nRT if you want to know the equation. So that little sneak path became a channel for hot gas, and it hit that rubber, which is a gasket just like in your car, and started melting it. Well, we didn't see this. These were post-accident pictures, because that would have shut things down before the SRBs went off. We wouldn't have any capability here, because with the SRBs, you're going to go to space. Maybe. But that was another sign in the post-accident photos that they said, okay, that was a major problem. So here's the burn through. Sadly, the radial position of the SRB where the burn came through was pointed right at the strut that holds the SRB to the external tank. There's only 2 of those per SRB, and it basically acted as a torch, weakening that strut. When that strut weakened, because of the heavy dynamic pressure, this is a 73 seconds, so you're traveling just short of the SRB separation, so you're doing about 2,000, 2,500 miles an hour. It pushed the SRB into the external tank, which is a fin wall, probably broke the hydrogen tank first, which is why you probably, I think, you see all the extra hydrogen gas mixing right there and burning with the rest. And then that explosion continued up, ruptured the oxygen tanks, and hydrogen and oxygen are hypergolic. When mixed together, they explode. And so that, unfortunately, was the result. We think, well, this image is not very good, but there's one, we think the capsule was over here to the side. The capsule was actually broken and pushed away. NASA found it, found the astronauts. 3 of them had tried to get into their emergency egress equipment. At 46,000 feet, I just looked it up, time of survivability is about 5 seconds. So they hardly had any time. More than likely, who knows what the compression did, but if they were still alive, then they were still alive. At least 3 of them were. So probably they all had hypoxic symptoms, which means you just pass out. Pilots go through altitude chamber training, and they pull the mask. We pull the mask off and see what symptoms we have when we start getting hypoxic, and then eventually you fall asleep. So they never did what hit them after the explosion. And if hypoxic deprivation didn't get them, then they crash into the ocean. Could it had been prevented? There was something called an RTLS, return to launch site, which theoretically you could punch off the external SRBs, but nobody ever tried it. It was a very dangerous maneuver. Nobody knows, and I've never heard anything official from NASA, whether they would let this happen or not. But if that happened, then you would still have energy to go up and then perhaps come back around. But where are you going to land? If you have enough to get back to the Kennedy launch site, maybe, but it's lots of suppositions. So Columbia was another, I think, a NASA failure. The external tank constantly had pieces of the chlorohydrofluorocarbon foam fall off, little bits and pieces here. That's what broke pieces of the shuttle ceramic tiles all the time. In this particular case, there was a big enough chunk that hit right at the leading edge of the left wing. And so when you came back in the atmosphere and that left wing is getting 2,500 degree temperature swings, now you've got basically a torch. Behind that is an aluminum wing, and if it's exposed, then that torch is basically burning the aluminum, which it did. And then it burned into a hydraulic system. How much? Probably quite a bit. It may have even had the hydraulic system fail. Now you don't have any control. You've got a wing that has an asymmetrical drag on it, so it's pulling the spacecraft this way. The yaw system is trying to pull it back, so the astronauts probably would have noticed an increase in yaw and firing of the thrusters to do this. But once you got that instability going, then the aircraft becomes unstable. And this thing cannot fly at any other altitude in the atmosphere other than straight level. So it had basically catastrophic structural failure. It broke the whole thing up. It was going about at least Mach 10 at that point over Texas, with very high temperatures on the wings, and so there was no hope. And NASA knew about the carbon problem, the foam problem, had tried to fix it many times, but had not successfully done it just yet. So that's where it came off, struck the wing, and that was the end result. So we lost 14 people over 30 years. In war, that's not very bad, but losing anybody is bad. Okay, I want to finish with this one little exceptionally successful program called the Hubble. The Hubble started in the 1970s. They wanted a space telescope to get well above the atmosphere so they didn't have atmospheric aberrations, clouds, rain, all that sort of stuff. Great idea. They were supposed to fly it in 1983. Budgetary problems, that's all there, budget problems. Technical problems, always had that. And then that delayed it. Challenger was supposed to be a bird that took it up. Challenger couldn't. So finally, in 1990, the Hubble finally got launched on Discovery. This is a big telescope. The mirror is 7 feet 10 inches wide. That's huge. And these mirrors are ground to high precision, very high precision. It's as big as a bus, so it took up most of the cargo bay. It was very expensive to build because it took so long and they had so many things that they had to fix. Hubble does more than just look at a star and measure different things, so you have different kinds of instrumentation. It was put up at 360 miles close to the outer region of the shuttle range, but close enough so it could repair or be repaired if necessary, which was one of the things they wanted to do. And there were 5 missions, and the big one was done by Dick Covey. It was supposed to be brought back by the shuttle and put in a museum. NASA says we can't afford it, and then they shut down the program and they can't bring it back. So maybe Elon Musk will save it. We'll see. Okay, so they put Hubble up in space. They turned it on. They took a bunch of pictures. I said, "Oh my goodness, we have a disaster on our hands." It was a major problem. They couldn't see anything worthwhile in the pictures. And NASA, the great space agency that had funded and put this whole thing on the map, all of a sudden had all kinds of dirt on its face. So they launched a 2-year investigation. Couldn't figure out why. What was the problem with this thing? They brought in an old head. Who were smart guys? Yes, old guys, right? So this old gent came up and he looked at the images and he says, "Well, that's a spherical aberration," which in astronomical terms means the damn mirror ain't right. It was supposed to be ground down to these kinds of precisions, but the outer edges were flat. Now, when you make a telescope mirror, it's not flat. It's parabolic, right? Because the light coming down here bounces right back to where it's being collected. But light over here has to bounce back up at an angle to that same collection point. And that only happens with a parabola. So it's very complicated to grind a mirror perfectly to a parabolic shape. Well, they didn't do that. Why? Because they dragged out old instrument equipment to save money, and somebody assembled it improperly. And I heard one story is that they assembled it with the English system. It should have been a metric system. I don't know if that's true. But they didn't do it right. So this guy says, "Well, that's an easy fix. All you need is a contact lens." That's what we all have, right? Well, I don't, but some of you might. So NASA said, "Okay." Well, they had to go back to Perkin-Elmer and say, "Bad boys, you got to fix this. You got to take that error and make it exactly the opposite in your contact lens," which they did. And They put it on, the company's shuttle, went up, took all the panels out, took out the parts that didn't work right, put in the new ones, and Hubble was perfect. This is an example. This is Messier 100, a nearby galaxy in our local neighborhood. It's only 55 light years away, but this thing is 107 light years across. And what's a light year? It's 5.88 trillion miles. There's 400 billion stars estimated to be in that galaxy. And this is similar to the Milky Way. Ours is about 100 light years across. We're a peanut. We only have 200 billion stars in our galaxy. And by the way, if you stick around for about 2.5 to 4 billion years, we're going to be married up with Andromeda, which is a pretty galaxy up there, a little farther away than this one, that's merging with us. And it's going to eat us up. But it has 1 trillion stars. I mean, space is unbelievable. So now Hubble is a crowning success. What does it do? It confirmed that our universe is actually expanding. Cosmology theorists are now thinking about all sorts of things. They found that black holes were common in in most of the galaxies. Some of them are even rogues. They're black holes wandering around in space. They have no galaxies around them. Don't run into those puppies, you can't see them. Found the most transient, the biggest explosion ever seen. Farthest galaxy, 13.6 billion miles away. Now 13.8, but James Webb thinks it might be 42 billion light years away. So think of a cue ball versus a basketball. And here's a math question for you. What's the volume of a sphere? I'll say 4.3 times r to the cube times pi. So with 1 inch versus 4 inches, that's 113 times more volume if our universe is really 42. Now, why is that important? You'll see in the movie in just a second. Exoplanets, we now have found 5,200 exoplanets, not necessarily all supporting life. Some of them are supergiants like Jupiter or bigger. Some of them are small. Some are too close, too far, they're not in the Goldilocks zone. But we have a bunch of them that are in the Goldilocks zone. They're fairly close to Earth. They have carbon, methane that could have life on them. And those are in our local neighborhood. My dog is thinking of killing myself. Those are in our local neighborhood. We can only see local stars, about 2,000 of them, within 100 light years. And our galaxy is 100,000 light years across. And we've got 10 or 15 galaxies in our local neighborhood. And 100 billion galaxies that we think exist in the known universe, not going out to 42 billion. When you think about it, 100 billion, that's 10 to the 14th power. Okay, so the guy that owned the shuttle of the Hubble schedule decided he wanted to try an experiment. And so, since he was the scheduler, he says, I'm going to point the Hubble at the most empty region of space. We're almost done, by the way, so don't run away. In fact, we got door prizes, so don't run away before that too. So he says, the emptiest region of space is where? He put a team on it. They spent 2 years looking at all the areas. You know how big space is? Well, they wanted something that was out of the galactic plane. If you're looking through the galaxy, obviously you're going to see all these stars that are going to work, right? So you want to go perpendicular to the galactic plane. And we're out on the far edge of it, so we don't have all that center stuff. Big bunch of gaseous clouds and many, many stars. So they pointed at this piece in space for 3 days, took all of these pictures, and they found 3,000 galaxies they never knew existed. And so they decided 10 years later to do this again at another area in space. And they did it for 11 days, and they found 10,000 galaxies. They did it again a few years later. They found another 5,500. These were so far beyond that nobody knew they existed. They had never been seen by a telescope before. So what is that? That's taking about a quarter of an inch at arm's length. That's the piece of sky that you're looking at, which is 1/10,000,000th of the entire sky, if you were to go this way, all the way around. 10 million times 10,000 galaxies, and that's only to the edge of the current universe. We don't know what's beyond that. So that basically is the crowning achievement of NASA. I didn't get to the stars. I keep telling kids, shoot for the stars. If you only land on the moon, then you're much farther ahead than somebody who sits on the curve, like my grandfather used to say, spit in one hand and wish in the other and see which one fills up first. So I didn't get to the stars. I didn't get to the moon, but I did get to fly with the astronauts. I did get to see a lot of great stuff. So you kids, make sure you have your goals and keep at it. Now, if you don't make the academy this year, go to college, do well in school, because the academy particularly likes students in college who are doing great, because they've already demonstrated that they can work at the collegiate level. And from all these guys in the 3 different academies, I can tell you it's well worth it. Just the band of brothers that you have. These guys right here are my band of brothers. It's a great society to be with. Okay, I want to show you a video, and then we'll get on.